Hello, students. Now this is section 9.5, the gradient and directional derivative. So this is kind of application of 9.4, which is the partial derivatives. And even the previous sections when we talked about the velocity and speed. So we're going to repeat this one now in a different style. All right, guys, let's suppose that this is our curve, which is f of xy. This is what actually z equal any curve in three-dimensional space. Now, what do we notice here in this this curve? Let's take a point on the curve, any point on the curve, like point AB, any point on the curve, which is AB. All right, when I differentiate the function partially with respect to x, guys, exactly what am I finding? When I differentiate it partially with respect to x, if the particle is here and the particle is moving on this curve, so when I differentiate the function partially with respect to x, if this is the x-axis, by the way, what I'm finding is the velocity of the object if the object is going in what? In the direction of the x-axis. So this is actually the partial derivative of f with respect to x. If I need to find, so this is one part. The second part is, if I need to differentiate the function with respect to y, what's going to happen? This is the y-axis, guys. The partial derivative of f with respect to, what does it mean? It represents the rate of change in the direction of the y-axis. So if this is y-axis going this way, so this will be fy, which is the rate of change of the function in the direction of y. Like we can say it's the velocity of the function or the speed of the object in the direction of the y-axis. So this is a nice interpretation of the meaning of what? Of the partial derivative. So when you find the partial derivative of the function with respect to x, you're finding the rate of change or the velocity or the speed of the object if the object is moving in the direction of the x-axis. The partial derivative with respect to y is the partial, this will give me the velocity or the rate of change of the function, or it's the velocity of this object when it's moving in the direction of what? Of the y-axis. Beautiful. But we all know that objects don't always move in what? In the x-axis direction or in the y-axis direction. So what if the object is moving in another direction? Which direction of that? So let's suppose, guys, that this is our direction. It's this vector here that you see here. Let's suppose the object is moving in this direction. So our object is here, is moving now in this direction. Can we find the rate of change of the function in this direction? Can I find the velocity or the speed of the object in this direction? Which direction? In the direction of u. Yes, we can. But to do that, first of all, we have to make sure that our vector u is a unit vector. So u has to be what? A unit vector. So now, what we're going to do in this section, the summary is as follows. We will be looking for the rate of change of the function in the direction of any unit vector u as you see in the graph. Or in other words, we are going to measure the velocity or the speed of an object moving on this curve represented by this function in the direction of the unit vector u. And this is, guys, the summary of everything in this section. Clear? So we know that the partial derivative of f with respect to x is the rate of change of the function in the direction of the x-axis. Partial derivative of the function with respect to y is the rate of change of the function in the direction of the y-axis, which both of them give me the velocity in these directions. But what if I need to find the rate of change of the function in different direction rather than the x-axis and the y-axis? So I have to give you which direction I want you to go through. So if you're going to go in the direction of u, then this u must be a unit vector. If I give you u, then definitely I can find the rate of change of the function in this direction, which means I can find the velocity of the object that is moving on this curve in the direction of the unit vector u. This is a summary of our section. To start doing this, we are going to compute today something called the gradient of the function. what's the gradient of our two-dimensional function, f of xy? It's simply a vector where the first component is the derivative of the function partial with respect to x, and the second one is the derivative of the function with respect to y, the partial derivative of the function with respect to y. And it's written like this, fx and fi, or it can be written as a vector in this form. Those are our vectors. So the gradient of the function is going to give me a directional vector, okay, called the gradient. And what is it equal to? It's equal to this. What does it mean? I'm going to explain it to you now, and actually it will be also explained in the next section. But I'm going to give you a hint in this section. What is exactly the gradient representing, and how is it related to the function f? So let's take this example, guys. If you have f of xy is equal to x squared plus sine y, I need to find the gradient at half and pi. Okay, what's the gradient of f in general? It's the partial derivative of f with respect to x, comma, the partial derivative with respect to y. It's a vector. So what is this equal to? fx, let's differentiate with respect to x, guys. What's the derivative of x squared? It's 2x. What's the derivative of sine y with respect to x? It's a 0. There is no x, so this is a constant, comma. What's the derivative with respect to y? The derivative of x squared with respect to y is 0 because there is no y here. This is constant. And the derivative of sine y is cosine y. So this is, guys, our gradient. You can write it also this way. It's 2xi plus cosine yj. This is the gradient of the function. What does this represent? I'm going to show you in a minute. Now he wants to find the gradient of f at the point half and pi. All right, that means we're going to replace every x with half and every y with pi. So this is equal to 2 times half I, comma, cosine pi j. So this is not comma, sorry, plus. And this is equal to I, and cosine pi is -1, so minus j. So here, this is the vector 1 and -1. So the gradient here is 1 and -1. Again, as I said, we're going to explain it later on. What do we mean by the gradient? All right. So this is the solution. Now, to find now the rate of change of the function f in the direction of u, and u is a unit vector, this is found by a formula called, here it is. This is the directional derivative of f at the point AB in the direction of u. Okay, so this is the directional derivative, means I'm going to find the rate of change of f, this function f, in the direction of u at the point what? AB. How do I find this one? It's simply the gradient of f at the point dot product the vector, the unit vector u. Very simple. We find the gradient at a point, dot product with the unit vector u. This will give me actually the velocity of the object who is moving in the direction of the unit vector u. All right, let's do this question now then, guys. I have this function. Graphing the function is not easy. I'm not going to graph it, but we're going to find the d of this one in the direction of this vector. All right, so how do you find it? To find this one, the formula says that the directional derivative of the function at any point AB in the direction of u is nothing but the gradient of f at that point dot the vector u. All right, the first thing you have to check, what is the magnitude of your vector u? Here's you guys. You know what's a magnitude? It's the square root of the square of the first one, which is a 3/4. We square the first component, plus We square the second component. The square of 1/2 is 1/4. If you add those, what do you get? 4/4, which is equal to 1. So what do we conclude here? We conclude that U is actually a unit vector. You must investigate this one first. Beautiful. Now, what do we find? We will find the gradient of f at any point AB. Let's say x and y. Let's find first the gradient. The gradient of f is, as you know, fx comma fy. All right, what's fx now? Let's go back to the function. What's the partial derivative of this with respect to x? The derivative of x squared is 2x, and we don't touch the y because we treat y as a constant. Now, what's the derivative of this one with respect to x? That's a 0, right? So done, comma. Let's differentiate with respect to y. What's the derivative of this term with respect to y? The derivative of y is 1. I'm left with x squared minus, what's the derivative of this with respect to y? It's 12y squared. This is, guys, the gradient in general at x1, y. So the gradient of the function at the point what? The formula says it's at the point AB. AB here is at what point? 2 and 1. At 2 and 1 is equal to 2 times 2 times 1, comma, 1 square minus 12 times 1 square. My apology, this is 2 square. X is 2. And we close. And this is equal to 2 times 2 times 1 is 4. 4 minus 12 is negative 8. So this is the gradient, guys. Now, what do we say? The directional derivative of the function in the direction of u at the point 2 and 1, it's equal to gradient of f at the point 2 and 1 dot u, the vector u. And the gradient, we found it to be 4 and negative 8. We do dot product with u, which is, I know it's a unit vector, root 3 over 2 and half. Let's multiply. How do you do dot product? We multiply the first component with the first component. So it's going to be square root of 3 over 2 multiplied by 4. Then plus the second times the second. So it's negative 8 multiplied by half. This 2 with this one is gone. So you have 2. So this is equal to 2 square root of 3 minus 4. All right. And this is our directional derivative. It must have a value which is negative, approximately negative 0.5. This is approximately negative 0.5. So what's happening since the direction derivative is negative? So that means the function is decreasing. Okay, or the speed or the velocity is reduced and is going in the opposite direction. So what's happening is that the object is moving backwards. Okay, this is the meaning of it. The function is decreasing in this direction. All right, let's do this one. This is a better example where I can visualize what's going on, guys, because I know how to graph the function. Now you have this one, f of xy is equal to x squared plus y squared. Let's call this one z, guys. I taught you in the previous section, especially in the first one, how would you graph something like this? How do you graph it, guys? We let what? We let z equal to 0. So what do we get? We get x squared plus y squared equal to 0. What is this? This is a circle of radius 0, which is going to be at the origin. So we are here. Now we let x equal 0. So that means z is equal y squared. This is the z-axis, this is the y-axis, and this is the x-axis. Z equal y squared is definitely that one. This is z equal y squared. Now we're going to take what? Y equal to 0. So z is equal x squared. Here's the x-axis, guys. So the curve is going to go like that, and it's going to go somehow beyond this. And what do we obtain from all of this? We're going to get actually like this paraboloid. This is the graph of our function in three-dimensional space. Now, we need to find the directional derivative. So we need to find actually the rate of change or the velocity of any object moving on this surface. You see that surface, that paraboloid? In which direction? In the direction of this vector u. U goes from 2, 1 to 4, 0, by the way. The vector u is starting from 2, 1, 2, comma 1, and it goes to, erase that one and fix it. And up to 4 and 0. 2, 1 and 4, 0. This is 2 on the x-axis, 1 on the y-axis, up to 1, 0. So I'm not going to graph this anyway. So what would be the vector u? You remember the vector u, we're gonna actually shift it, put it onto the origin. So we know the vector is going to be what? Remember? So it's 4 minus 2. We subtract this, comma, 0 minus 1. If we subtract that, we get 2 and negative 1. So our vector u now is this, 2 and negative 1. But if you measure the magnitude of u, you will notice that this vector is not a unit vector. Why? Because the magnitude is the square of the first component, which is 4, plus the square of the second component, which is 1, and this is a square root of 5, which is not equal to 1. So that means u is not a unit vector. But how do I make it unit? We take something called u hat. Remember, it's u itself divided by its magnitude. If I divide a vector by its magnitude, this will make it a unit vector. U now, so you have 2, negative 1 divided by square root of 5. So this is going to be 2 over root 5 and negative 1 over root 5. And by the way, if you compute this one as a value, so this is almost 0.9 approximately, and negative 0.45 approximately. All right, so this is our unit vector now. Let's see where is the unit vector on the graph, guys. So I'm going to take the unit vector with a different color. So let's take the u. X is 0.9. If this is 1, 0.9 is somewhere here on the x-axis. And y is negative 0.4. So y is negative. So it's going to be, if this is negative 1 on the y-axis, so it's almost here. So they meet at this point. So this one actually, by the way, is our unit vector. You see this one? This is our unit vector. It is in length 1. So what's happening now, guys? There is an object who's moving on what? On the surface. Where exactly on the surface? I need to find the velocity of the object on this surface. At what point, by the way? At point 1 and what? And negative 1, right? So look what I'm going to do now, guys. I will take the function f at 1 and negative 1. But we know that this is z, isn't it? So let's plug it in. So it's going to be 1 square plus minus 1 square, which is 2. So what do we have, guys, here? When x is 1 and y negative 1, what's z? Z is 2. So let's plot this one on the curve. I'm going to change the color. X is 1. Here is x is 1. Y is 1. Sorry, y is negative 1. This is negative 1. So 1 and negative 1, they will meet somehow here. This is the point 1 and negative 1. But z is 2. So what do we go? We go with from this up to 2 on the z-axis. Then we go parallel to the x-axis and see where it meets here. So this is the point. So what's happening, guys, here? At this point is 1, -1, and 2. There is an object here. This object is moving around on this surface. We need to find the directional derivative. Okay, how do you find the directional derivative? Before I do that, I'm going to explain to you what's the meaning of the gradient. So let's find here the gradient, guys. What is the gradient of f? The gradient of f, we know it's fx comma fy, which is equal to the derivative with respect to x is 2x, right, comma. The derivative of f with respect to y is 2y. This is the partial derivative with respect to x and 1. So the gradient of f at the point 1 and -1, what is this, guys? So replace x with 1, you get 2, and y with -1, you get what? -2. I am going to use another color here. So I'm going to choose, for example, this brownish thing. x2, here is 2, and y -2. If this is -2 on the y-axis, where do they meet? They will meet here. So this is 2 and -2. What is exactly the gradient? Go back to the point, guys. You see, this is your gradient, huh? the brown one. Put it there and make the same vector. So actually, this is the gradient of f at the point 1 and -1. So what's the gradient, guys? It is the vector that is perpendicular to the surface at the point 1, -1, and 2. This is how you understand what the gradient is. So that means, by the way, this vector is going in the same, almost in the same dimension as you. Do you notice that? That we're in the same dimension of you. So the vector now, the gradient, is the vector that is perpendicular to the surface at this point that I am pointing at here. Okay, now let's find the directional derivative. What's the directional derivative of the function f at the point 1, -1 in the direction of u? What is this? This is the gradient of f at -1, 1, sorry, at 1 and -1 times u. But the gradient, we found it to be 2 and -2, dot u is 2 over √5 and -1 over √5. And if you multiply, you will get dot 2 times 2 is 4 over √5. Then -2 times -1 is 2 over √5. And this is 6 over √5. This is, guys, the velocity of the object who's exactly here at this point. Going in which direction? In the direction of u. This is our u. See that? It's going in the direction of u. This is exactly the velocity of the object that is on this surface going in the direction of u. It's in this direction. See? Now, beautiful. Now we started to visualize and understand what's going on, right? So this is the directional derivative. So you're finding actually the velocity or the speed of the object who's actually now exactly at this point. So this is like what we say instantaneous velocity. At this point, exactly at this point, what is the velocity of the object? It's this. In which direction is the object moving? The object is moving in this direction, going in that direction, period. So this is physically what's going, mechanically is what's going on this example. All right, let's compute this one, guys. Now this function is, for me, is impossible to graph. I have to have a software, so I'm not gonna really explain much here, except that he says compute the direction derivative at the point 1, 1 in the direction of this unit vector. We know that u is a unit vector, by the way. Let's look at the magnitude of u. Let me check it with you. It's the square root of the square of the first plus the square of the second. And we know that sine square plus cosine square is 1. So now I know it's a unit vector. But I need this vector in at what? At pi over 6. So what's u now? U is the vector cosine pi over 6, comma, sine pi over 6. And this is equal to cosine pi over 6 is the square root of 3 over 2. Sine pi over 6 is half. Check it, you would find that also this vector is a unit vector. Take the magnitude, you get 4 over 4, 3 over 4 plus 1 over 4, which is 4 over 4, and it's a unit vector. Perfect. Now, what do we need to find? We need to find the gradient of f first. What's the gradient of f? It's fx, comma, fy. All right, what's the partial derivative of this function with respect to x, guys? We only differentiate x squared, which is 2x, and we keep y. Minus, what's the derivative of this with respect to x? It's a 0, so that's it. This is fx, comma. Now, what's the derivative of this with respect to y? The derivative of y is 1. I'm left with x squared minus the derivative of this with respect to y is 12y squared. This is the gradient, guys. Now we need to find the gradient of f at what point? At the point 1 and 1. Because he wants the directional at this point, so we're going to plug 1 and 1. So this is 2 times 1 times 1, comma, 1 square minus 12 times 1 square, which is equal to 2, and 1 minus 12 is negative 11. This is the gradient, guys. Now, can we find the directional? Of course. Now, the directional derivative of f in the direction of u at the point 1 and 1 is nothing but the gradient of f at 1 and 1 dot u. The gradient, we found it 2 and negative 11 dot u here is root 3 over 2 and half. Let's multiply, guys. How do you multiply? The first by the first. So 2 times root 3 over 2 is root 3. And minus 11 times this is minus 11 over 2. This is exactly what you have for the gradient, the directional derivative. All right. So this is a different value probably. So what we have is 6 and y. Okay, there's a fix this one. Now let's go to the next part. Find the maximum and minimum rate of change. Now, let's talk about what's in this slide, guys. Remember, the object is moving in the direction of what? In the direction of u. Fine. Sometimes you'll be asked, if I'm giving you the function or the curve or the surface that the object is moving on, can you find the maximum velocity or speed of this object? Yes, we can. What is the maximum? The maximum is going to be the gradient, the magnitude of the gradient at that point, by the way. As simple as that. Okay, but in which direction is this object going? This object is going in the direction of the gradient itself. So look what happened. If the gradient and you are in the same direction, like the example we did a minute ago, so what's the angle between them? The angle between them is 0. If the angle is 0, that means the gradient and the vector u, the unit vector, are going in the same direction. So I'm going to replace u with what? With the gradient. But the gradient could not be a unit vector. So what do? I'm going to divide it by its magnitude. And what do we get now? We get our unit vector. So in order for us to find the maximum speed of an object moving on the surface, z equal f of xy, how do you find this one? Simply, it's the magnitude of the gradient at that point. This is the maximum speed. In which direction we're going? This is going to happen only if the object is moving in the direction of what? Of the gradient itself. Remember, what's a gradient? It's a vector that is perpendicular to the surface at that point, isn't it? And this is how you explain it. If I need to find the minimum speed, it's negative, guys. This is the minimum speed. And which direction now? In the direction of the negative. So if the object is going in the opposite direction of the gradient, then this will give us what? A minimum speed. Alrighty? So the object is here. U, for example, is in this direction. If U and the gradient are in the same direction, if U and the gradient, remember the gradient is this is the gradient of F, it's the vector at the point AB. This is the vector that is perpendicular to the what? To the surface at this point. So if this vector and U are going in the same direction, so what's going to happen here? What's going to happen here is that this object will have the maximum speed. So what's the minimum speed? The minimum speed will happen only if the U and gradient are going in the opposite direction. You see, U is going in this direction. If U is going in the negative direction, so this U now is going to be a minus gradient over that, then we're going to get what? The minimum speed. Let's look at this same example we did a minute ago, but I'm changing the things here. So look what's happening here. I have Z is equal to, so we have F of xy is equal to x squared plus y squared. So remember the graph of this one. Hopefully we can get a picture of what's going on. Z, Y, and X. We know that the graph looks like this, right? We know that the graph looks like this. It's a paraboloid that is open upwards. Alrighty. So this is the shape of our function. We already know this one. Now, let's take, he wants to find all of this at the point 1 and 3. So this is X and Y. So here, Z is equal to x squared plus y squared. So if I take x to be 1 and y is 3. So now, when at the point 1 and 3, this implies that Z is equal to what? 1 square plus the 3 square, and this is 10. So what's the point here? When x is 1 and y is 3, Z is what? Is 10. How do we graph this one, by the way? X is 1, y is a 3. So they meet here. This is 1 and 3. But I need 1, 3, and 10. So what do we say? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is 10 on the z-axis. What do we do? From y, which is a 3, we go all the way up to z equal to 10. Then we take a line parallel to the x-axis and see where do they meet here. They will meet somehow here. So this is the point, guys, that we're looking for. So I'm going to remove now those things. We don't want them. They will distract me while I'm working. Alrighty. All right. So we don't need this anymore. Something. Okay. So now let's take the pen and make the graph again. This is our graph. And this point, let me put the point a little bit down so you can see it on the surface, or I can actually extend my surface so you can see it. So if we go a little bit up higher, so I'm going to go with my graph a little bit higher, guys. Okay, so this will go higher. So the graph will look like this. So I just took it a little bit up. So I can see where am I on the surface. I'm here. What's this point? This is 1, 3, and 10. 1, 3, and 10. So the object now is on this point, at this point on the surface. Now, What's the maximum speed? Let's look at our vector u. This is our vector u in the direction of u. Now, what's u? U is equal to, by the way, he just wants to find the direction derivative. U is equal to 2 and 3. If we check the magnitude of u, we will find that this is the square root of 4 plus 9, which is equal to the square root of 13, which is not 1. So what should u be now, guys? It should be 2 over root 13 and 3 over root 13. Now, this is a unit vector. Fine. Now, what do we find from this one? To find the gradient, to find the directional derivative, we need the gradient of f, which is fx comma fy. We know that fx, we already found it, it's 2x, and fy is what? 2y. The gradient of f at the point 1 and 3, we're going to find the gradient because he wants it at 1 and 3, is what? We will place x with 1 and y with the 3. And this is going to give me 2 and 6. Okay, where is the gradient, guys? Here is 2 on the x-axis, and here is 6. 2, 3, 4, 5, 6. So this is the gradient. This is the gradient of f. But it has to be where, guys? It has to be on the surface. So this is actually the gradient of f at the point 1 and what? And 3. So here is the gradient, guys. This vector, by the way, is perpendicular to the surface at that point. It's like, imagine there is like a water coming up from this hole, go straight. This is exactly the gradient. Now, what's the directional derivative in that direction? The direction derivative of f at the point y and 3, it's equal to the gradient f at 1 and 3 dot u. And the directional derivative is 2, 6, guys. Dot u is this one. So it's 2 root 13, comma 3 and root 13. If I multiply these two, guys, what do we get? 2 times this is 4. Sorry, there is no vector here. This is supposed to be a scalar. So this is 4 over root 13 plus 6 times 3 is 18 over root 13. And this is equal to 22 over square root of 13. This is the velocity of the object that is going in the direction of u. U is the same as that. It's 2 and 3. 2 and 3. Here is 2 and 3. So this is mainly u. So if the vector, if this object is going in the direction of u, right, in the direction of u here, the velocity is what? What's the direction derivative? 22 out of square root of 13. This is the velocity of the object if the object is going in the direction of what? In the direction of u. Okay. Now the other part of the question says, what would be the maximum and minimum speed? Let's do part B now. We know that the maximum minimum, let's talk about the maximum speed. What's the maximum here? The maximum, according to the theorem, it's the magnitude of the gradient of f at what? At the point 1 and 3. But the magnitude, the gradient, we found it to be 2 and 6. So what is this? This is the square root of the square of the first, which is 4, and the second one is 36. And if you add this, this is the square root of 40. So if the object, by the way, is going in this direction, in the direction of the gradient, okay? Actually, the gradient here, unfortunately, is not a unit vector. So the maximum, here is the maximum. In which direction? Of u. What's u now? It's the gradient of f at 1 and 3 divided by what? By the magnitude of the gradient of f at 1 and 3. I'm just trying to make u, the gradient, a unit vector, which is actually 2 and 3, sorry, 2 and 6, this is a gradient, divided by the square root of what? You know, the magnitude of this one is 40. So this is going to be 2 over root 40, comma, 6 over root 40. So if the object is moving in this direction, which is actually the same direction as the gradient, right? Then it will have a maximum speed. Will it have a maximum speed in this direction? So let's look at this direction. In this direction, actually, this is the directional derivative of f in the direction of u at the point 1 and 3. Is this the maximum speed? No, this is not the maximum speed. Where is the maximum speed? Here is the maximum speed. If the object is going in this direction, you will have a maximum speed of what? Of square root of 40. So accordingly, we can say that the minimum speed is what? Same thing, guys. It's going to be minus root 40, because the object now is going to go in the other direction. So maybe we can change this one in different color. Let's take the green one. So if the object is going in this direction, negative, all right, the velocity will be minus 40. And this is in which direction? In the direction of u minus u, which is equal to negative 2 root 40, comma, negative 6 over root 40. So if the object is going in the opposite direction of the gradient, then the velocity will be the minimum, which is negative 40, negative root 40. And this, guys, represents exactly two things. So what did we do here? The summary. We were able to understand what's the meaning of the first and the second derivative, right? Partial derivatives. So we started with the first and fx and fy. We said to differentiate the function partially with respect to x, that means you're finding the speed of the object moving on the curve in the direction of the x-axis. The partial derivative of f with respect to y, what does it do? It gives me the velocity or the speed of the object if it's the object's moving in the direction of the y-axis. So what did we do in this section now? We were able to find the speed or velocity of the object if the object is moving what? In any other direction. Which direction? It has to be in some direction of some unit vector u. And this is the summary. And at the end, we were able to find the maximum speed and the minimum speed. The minimum speed of an object is a curve where if the object is moving in the same direction as what? As the gradient. The minimum speed is happening if the object is moving in the opposite direction of the gradient. This, guys, summarizes everything in this section. I hope you understood it. It's very interesting to know how can we find the maximum and or the speed of an object moving on the surface like a plane on the air. Can you find the speed of that plane? Yes. All I have to do is to, while I am on the ground, I can actually look at the direction, get on the ground any unit vector in the same direction, and apply the directional derivative, which is d formula. I will get the speed of the plane. Imagine, all I have to do is to look at the plane and see which direction it's going. I'm going to construct a unit vector on ground in the xy plane in the same direction as the plane. Take this vector, apply it to the formula, and this will give you the speed of the plane. Of course, if you have what? The path that the plane is flying on. So if you have the path that the plane is flying on, can you find the speed? Yes, simply take a unit vector on the ground in the same direction as the plane, apply it to the formula, you're done. You can find the speed of the plane. Interesting to know this. Actually, I like to understand exactly what's in here, and this is a nice, really method of finding the speed of an object, whenever it's flying to, wherever it's moving in any direction on Earth. I hope you enjoy it. You guys have a good day. We'll see you in the next one.